Hey folks, how we doing? This is Mr. Murray coming to you with a do now for Monday, May 11th, 2020. Welcome back to another wonderful week of learning remotely. I'm excited to continue to bring you guys at Course One Honors some amazing math to really keep the challenge going and to keep providing you a new stuff to explore during this really important year of your mathematical journey. Um, so what I have here is this is building on the do nows that I've been doing over the past few lesson days. I recommend going back and taking a look at some of my past couple days. So I'm thinking last Friday, I believe it would be the 8th, and it's the Thursday the 7th, right? Maybe taking a look at those because I think I had some examples last week of me graphing through some of these examples. So what I want you to do is take a look at this. Now this is coming off the Hangout from Friday. So we have the function -3 times a third to the power of x plus 1. So what you're doing is using what you know about exponents, you're plugging in numbers for x, you're generating a table, and you're using that table to make a graph. Now you don't have to put in a lot of points. Once you start to find points that either go towards a number and get really close and you can't graph them because they're like a fraction, or if you find numbers that are so big or so small they go off the graph, right, you obviously can stop going in that direction as well. Okay, so please take a moment, pause the video, complete the table and graph, then when you're ready, unpause, and you can see what I got. Okay. So the idea is, again, it comes down to this. It's just another different kind of function. And like with every function, we need to make a table. Okay, so I build my table, and I start by plugging in 0. Anything to the power of 0 is 1. So a third to the 0 is 1. -3 times 1 is -3. -3 plus 1 is -2. So 0 goes in, -2 comes out. So 0, -2 has to be on the graph of the function. Now I plug in 1. 1/3 to the power of 1. Anything to the power of 1 is itself. So a third to the power of 1 is a third. -3 times 1/3 is -1. -1 plus 1 is 0. What if I plug in 2? So a third squared. I'm going to do this one now because this one's harder to do without writing it down. So 1/3 squared equals a third times a third, which is a ninth. -3 times 1/9 equals -3/9 equals -1/3. And -1/3 plus 1 is equal to 2/3. Okay, because you can think about taking one of the 1/3s off, so breaking off a third and canceling it out with this third, and then you have 2/3 left. So this would be 2, or you could use your calculator to verify that as well. Interesting. So it's not a whole number anymore. Okay, now when you do the power of 3, you're going to get 1/3 cubed. So you're going to get 1/27 times -3, which is equal to -3 over 27, which is equal to -1/9. And -1/9 plus 1 equals positive 8/9. And if you do 4, maybe you see the pattern, you're going to get 26/27. So you're getting very, very close to 1. But at this point, we're done because, 26/27, how do you graph that? That's almost 1, right? 5, for example, is going to give us 80/81. 6 is going to give us 242, 243. So we want to stop really going in that direction. What about negative 1? So when I do a third to the negative 1, first I'm going to flip the third, and then I'm going to take the negative and make it a positive. So it's 3 over 1 to the 1, but 3 over 1 is 3. It's actually, yep. So it's 3 to the 1. So it's 3, and then I do 3 times negative 3 becomes negative 9, and negative 9 plus 1 is negative 8. And then if I was to plug in negative 2, then it would be 3 over 1 to the 2, which would mean it would be 3 squared, which means this would be 9 instead of 3, which means I would have negative 27. So that would give me negative 26, and that won't even fit on the graph. So I stopped going in that direction, but I know it's going to continue to go down. So I plot, I've got 1, 0, I've got 2, those with 2/3, and it's getting really close to, but not equal to 1, right? 242, 243 is really close to 1, but not equal to 1. And it's kind of not the best graph, my apologies, but you can imagine how hard it is to draw that kind of phenomenon with the marker, with a pen, so to speak. So that's the idea, though. With these kind of functions, mathematically, there's a number that it's approaching that it's going to get really close to but not hit, and that is represented by what we call the horizontal asymptote, right? You can see 242, 243. Then the next one's going to be 728 out of 729. It's always going to be really, really close, but never equal to 1. So I thought that I would take some time and I would analyze it, because I made a similar table here, and see if we could find the domain, range, intercepts, where it's increasing, where it's decreasing, what its horizontal asymptote is, where it's positive, where it's negative, and its end behavior. So this is that same graph. It comes up and it starts to vanish at this point. So, or not vanish rather, but starts to level off. So the domain, as always this year, with that is like with parabolas, with lines, with absolute value, negative infinity to infinity. The new thing with this is the range. So on one side, we're always going to have some form of infinity. In this case, it's negative infinity, and I know that because of the downward facing arrow. And then there's going to be a max number. In this case, there's 1. But the difference here is we're now going to put a parenthesis on the 1. And the reason we put a parenthesis on the 1 is because it never actually gets to a value of 1, right? Remember we were saying it gets to 242, 243, 728, 729, right? Whatever. And then if you can keep going and going and going, even eventually, as you continue to go, right, you could get like a really big number. Like you could do 3 to the power of 100, and it's going to basically be like 3 to the power of 100 minus 1 over 3 to the power of 100. Okay, and you can imagine that basically that number is so close to 1 that your calculator is going to tell you it's 1. I actually just did it, and it told me 1. But in reality, the numerator is not really equal to the denominator, so it's not really 1. So it never actually reaches that value, and so you never put a hard bracket on the number side of the range with an exponential function. Okay? Y-intercept and x-intercept. So it touches the y-axis, at 0, -2. It touches the x-axis at 1, 0. Now, y-intercepts are not, x-intercepts rather, are not guaranteed. Some functions never reach a value of 0. 2 to the x never reaches a value of 0. 1/2 to the x never reaches a value of 0. So that's not guaranteed to happen. A y-intercept is guaranteed to happen, because if you say the domain is -infinity to infinity, then you're saying you can plug in whatever you want. So if you can plug in whatever you want, you can plug in 0. So you're going to have a y-intercept all the time. You just want to see what happens, right, as always, when you plug in 0. Where is it increasing? In this case, it's increasing from -infinity to infinity. It's increasing everywhere. So I just literally put the whole domain, and it's decreasing nowhere. All right, horizontal asymptote, we're going to write y is equal to 1. And that asymptote, remember, is the line that is coming up right next to, but it's not touching. Let me even make that dotted so we can see. Hopefully see if we can see through that line. Right, coming up right close, but not touching. So, and we can see it goes through 1. It's always going to be a y equals, because it's a horizontal. Okay, or if someone tells you, can you write it in f of x notation? Correct, f of x equals 1. Okay, positive and negative. Where are the y values positive? Where is it above the x-axis? Where is it below the x-axis? I'm just going to delete this so we can see that one. So it's positive. Remember, this is always x values. So starting when x equals 1 and afterwards, the y values are positive. And before 1, the y values are negative rather. So here's 1. Before x equals 1, right, y is negative. When x equals 1, it's 0, and that's why these are soft brackets, because it's not positive or negative. And then after 1, the y values are positive. All right, end behavior. Here's the tricky part. As x goes to positive infinity, negative infinity, let's do negative infinity, f of x goes to negative infinity. And I know that because it's pointing down. As x goes to positive infinity, f of x is going to go to 1. And I know it never reaches 1, but what happens is it's the idea that it gets close enough to 1, okay? And so this is the idea of limits that you're going to learn when you start to get into calculus later in high school. But we're trying to get a sense of where is it going? What are the outputs trying to become? Are they trying to become a number? Are they trying to become infinity? What's going on? What's the pattern there? Okay, and so like I said with my calculator, right, it was already calling it 1 when we plugged in 100, and so that's giving you a sense of the direction it's going. It's getting sufficiently close, but not necessarily equal to 1 as x gets larger and larger and approaches infinity. This analysis is something we're going to continue to do throughout this unit because it's important to be able to do analysis with every function. As we do it, think about some of the common themes that we see from function to function, because if you can use those common themes, just like with quadratics, if you can use those common themes to your advantage, you're going to find this a lot easier. All right, keep it up. Best of luck, and make sure you check out the materials for today. Until next time, have a wonderful day.